Okay, so we got through some of the exercises. I think we finished until here, and there are a few more exercises left on uh, implementing functions like these. And then we have, I think, Einsum. Yeah, and then we'll be done with this. So the goal for this stream is to basically finish the rest of the notebook. So I'm going to open this on Colab. Okay, why can't I open this with Colab? Is this a private repository? No, it isn't. Yeah, yeah, let's connect. We have disabled AI completion, and we need to run until here. Oh yeah, meanwhile you can read this question, find class for accuracy, we have scores. Okay, so let's find top classes, argmax, along the dimension 1, and right now I just need to find out uh, correct prediction or all predictions. Yeah, what are the correct predictions? For that, we can just do top classes equals true classes. Maybe we should call this predicted classes, and the accuracy would be average, mean, Yeah, this should be it. Carpool. Hmm. Let's just do this. Yeah, yeah, makes sense. Let's do the next one. Total price indexing using the torch dot gather function. You can read about it. The docs here. There's the index library. It's designed to provide indexing features motivated by how Einops works. Hmm. Let's see if gather is confusing. Can access specified by dim, tensor, dimension, and index. So if you have a 3D tensor as input, and if dim is 0, the output tensor specified by this. Hmm. So you have indices, you have a dimension along which you want to gather, and you have the input tensor. I don't think I fully understand intuitively what this is doing. Uh, hmm. So if you have log props, you have the correct labels for the next tokens. Hmm. If you use index, this is what you want to do. You want to index into log props using labels. The last dimension. Hmm. Normal PyTorch, not using gather. What index does under the hood. So this is the first dimension indices. This for the second dimension. All possible numbers for the patch. Index all possible numbers for sequence positions. Then all possible labels. Hmm. Okay, I think I have some basic understanding now. So you have prices, okay, for each kind of item, the tensor of items purchased, and the total price. So you want to use prices as your index tensor and to index into items. And do that by doing do.gather items dim equals 0 prices. What this is basically doing is, if you have an output of I is basically items of prices of I, right? Wait a minute. Should it be something like this? Suppose you have prices as 1, 5, 10, and you have items as, okay, there are three kinds of items. So let's say you bought 1, 1, 1, then you bought 3, then you bought 2. Right, so output should be this should be 0 next. So this should actually be 0, 2 and 1, and output would therefore be prices of shape prices, sorry, of shape items. You just need to return the sum. This should work. Yeah. Yeah, let's see. Okay, this is that indexing, not sum for them. Makes sense. Gather 2D, so matrix nav. The test already passes. Okay. Tell shop to write 3 asserts relating the arguments in the output. Right. So essentially what we're doing is out of I of j will be equal to matrix of I of indexes of I of j. So one thing we can say about out is it should have the same shape as matrix in index 0. You also know that indexes dot shape of 1, which is the dimension we are indexing over, max should be equal to the maximum value in that dimension of indexes should be equal to should be actually less than the max. Yeah, should be less than matrix dot shape 1. So if the first dimension is of size, let's say 10, so in that dimension indexes can only have values between 0 and 9. So it should be actually less than, it should also be this. And it is also the case that this is more accurate, and also that zero should be equals hmm, is this reasonable? Right, so the matrix and the indices should have the same number of dimensions. The shape of 0 is less than or equal to matrix of shape 0. But that shape should be equal to index shape. I thought it should be equals. Need not be equals because this was less than n. This would be less than n, which is fine. Okay, doesn't have to be equal, because we can also have okay. And finally, same thing as total price indexing, but I did use gather there. So this is basically gather. Yeah, makes sense. Okay, now we move on to indexing. Return the values at each coordinate using integer array indexing. Right, so we have a matrix n dimensional. We have two dimensional. Okay, we have a 2D cohorts tensor. What we need is something like output of I equals matrix of cohorts of I. So I guess if we just do this, return matrix of cohorts, it should work, right? Index 4 is out of bounds. Can I do this? Why is this so tricky? If I just do so if I do this, then it should return the first row of what I'm looking for. What I mean is, so I just need to do this and let me confirm this. Print codes of 0. Also want to print this. I just want to print. Right, so the 0, 1. This is my matrix. Oh, wait a minute. Expected element at 0, 1. So it should be 1. But this is wrong. Uh, this is what should have been. Let's look up teacher array indexing. Let's go back. Uh, hmm. And the index consists of as many integer arrays as dimensions of the array being indexed. Say a 5 by 7 matrix, and you're using two integer arrays 0 to 4, 0, 1, 2. Hmm. Guess then it would be uh, so the first row should be quotes 0. This should be the first entry. I'm stumped. Hmm. I would like to see the solution for this. Ha! That's close. Have to make it a tuple. So once you do a transpose, you have n by batch, but you can index using a tuple of arrays. I can get. Hmm. Ha! It's okay. That was a bit tricky for me. Right. So this works because let's say you have, yeah, let's say you have matrix as 0, 1, 2, 3, 4, 5, 7, 8. Then you have chords as, so you have this. Maybe we can add one more. So what you want is, how you want to get them is pass something like this, uh, something like this, and here you'll get all the rows, and here give all the columns, which means if you do coords or transpose, that's what you get. So you get 0 comma 0 comma 1 comma 2, these are all the rows, and then you get 1 comma 4 comma 4 comma 2, these are all the columns. And once you do a tuple of this, what you get is two integer arrays. Yeah, basically these elements, and once you do out of this tuple, you get uh, you first get what's in 0 comma 1, and then 0 comma 4, and then 1 comma 4, and then 2 comma 2. So you basically get what you need. 0 comma 1 is 1, 0 comma 4 doesn't exist. Oops. Should I have had something else? Maybe 0 and 2. So 0 comma 0, and then 1 comma 2 is 5, then 2 comma 2 is 8. Yeah, and yeah, this is exactly what's happening with this. This is an metric. Okay, anyway, yeah. So let's do the next one. Patch log sum exp. For each row of the matrix, compute log of sum of exponential of row in a numerically stable way. So you have these many rows. Each row is an n length vector. Do not use the inbuilt function. Right. So what's the problem in doing it the most obvious way? Let's see. So if I have matrix of, let's just say, one row, yeah, something like this. Let's say we all have really big values. Right, so the problem would be, the first thing you want to do is element-wise exponentiation, and there's your problem. Yeah, so that's not something we want to do. And similarly, if we had really small values, again, it's not numerically stable anymore. Exp of that would be basically 0. You can still have 0, and then you get log of 0. Yeah, so what you can do is you add and subtract some constant c to each element. So what you do is 1000 plus c, 1000 plus c, 1000 plus c. Now let's switch things up. Let's say we have few big numbers, really big numbers, and few really small numbers. So uh, what's a good c to have? It could be maximum. No, it can't be the maximum, and it can't, because they get even bigger. It can't be the minimum because this will get even smaller. So So what if you do so what we're doing is log of a power a plus a power b power c and can I take uh, the average? So I hope you see these two are equal. So if these two are equal, we need to choose C such that um, these things are numerically stable and what if we divide them by C instead of adding? Power A by C. Oh, let's look at one of these links. Uh, hmm. Wait a minute. This is log of sums. Right, so this is log of sum of exponents. And what you need to do is take the max, subtract it, so what you need to do is something like this, I guess, and C would be max of all the elements, which would be 1000. So in this case, we'll have log of a power 1000 minus 1000 plus a power 1000 minus 1000 minus 1000 minus 1000 minus C, which would be log of 1 plus 1, 2, basically log 2 minus 1000. I wonder if this works. Uh, yeah, let's find C for the matrix. P max time function would be 1. Uh, and what you need to do is x minus C dot x dot sum dot log minus C. Oops, it should be plus C because going minus here. Yeah. Mm-hmm. Let's keep our dimension. So this would be 2 comma 4. Yeah. They're not the same. Guess I might be doing by 2. How can that be? So do not keep the connection. So let's keep the dimension and still a lot of reference. Okay, I need to look at this. Uh, so, this definition. Y equals this, pairwise this, subtract some constant. That's basically what I'm doing, right? Hmm. exactly what I'm doing, or so I thought. P matrix is of yeah. Was an issue with the shapes. You need to be a bit careful. Let's see what they've done. Maximum last action. Yeah, unsqueeze it and do this. Makes sense. Now we have to do patched softmax. Hopefully we can do things faster for each of the matrix compute softmax. Hmm. We can use softmax is basically e power xi by summation of over e power, yeah, summation over e power xi indexed over I. And if we have log of this, take log of this, e power xi divided by log of this. Makes sense. So let's do patched logs x. Then let's do matrix divided by matrix minus. Uh, the observation is this: if you have e power a by e power p, or summation over e power xi, then you can just take log and then take exponentiation, and that would mean you get e to the power a minus log sum x. x. Let me show this in a better way. I guess I can just write the code. I mean, we can use this. So I want to calculate this for each element across rows. Um, One way I can do it is take log on both sides. So I get on the right hand side I get log of e to the power zi divided by log of sum of exponents, uh, exponentials, and yeah, if log a by b is log a minus log b, and log of a is just zi, log of b here is log sum x, which we already have a function for. So what I need to return is, so that's the log of what we need. So we just need to do e power zi minus the log sum x for each value. So p matrix x, which is matrix minus log sum x. I can unsqueeze this to enable broadcasting. Yeah, got it. So have done, oh, they've done this straightforward. Hmm. Now do patch log softmax, compute log of softmax for each row of the matrix. Yeah, so softmax is invariant to uh, any additions. So if you just add some constants here to each of these uh, values in the vector, then the softmax output still wouldn't change. You can see they cancel out nicely. Um, so I guess if you're doing softmax, you can add something to the row so that, yeah, so that it's numerically stable while not really affecting the answer. So first, I could just do then. I need to do this. Yeah, yeah, this is pretty much what we're doing. Log of a by b is log a minus log b. So yeah, this is what they're doing essentially. Let's do the next one, cross entropy laws. Okay, so we have logits, shape, patch, comma classes. We have true labels of shape, patch, and we have to return the laws for each example. And the hint is to convert logits to log probabilities. Right. Ah, okay, that's pretty cool. So yeah, so I can just find patched log softmax of your logits. This gives you log props because it's log of softmax. And now you need to find out the cross entropy loss. Since you know the true label, just need to look at the log probability for the true label. Just flip the sign because you need the loss. Um, that would be written um, gather from log props shape patch comma classes uh, cover index 1 use true labels as your indices and just flip the sign. Yeah, so this would give you yeah, this should work. Potentials dimensions. Okay, so think we need to unsqueeze it. Right, we need to unsqueeze true labels. Ah, and then squeeze it back. There must be a better way to do this. Let's see. Log probabilities and squeeze. Get the predictions. Squeeze. Yeah, I guess could be worse. Okay, yeah, we're close to finishing this. Let's do this. So we need to collect rows from a 2D matrix. Matrix of shape m cross n. We have row indices, shape k, which values in okay, be straightforward. of row indexes and take all the columns. Yep. And now duty matrix whose columns are taken from the input matrix in order according to column indices. Uh, don't see why this should be much different. So take all possible rows, but take only these columns. Yeah, let's look at the solutions. Yeah, it's as expected. You don't need this. Yeah, makes sense. Now we have Einsum. Okay, let's read this. ISO function. You'll need it a lot. This to work differently. Okay. Oh. 3 key rules. All right, focus. Repeating letters in different inputs means those values will be multiplied and those products will be in the output. So here you have ij is repeating, those values will be multiplied and will be in the output. So multiplying every element by itself, I mean multiplying elements pairwise, not pairwise, element-wise, multiplying element-wise. Omitting a letter means that the axis will be summed over, saying for each row, sum over all the columns. Yeah, across rows. You can return the unsummed axis in any order. It's like permutate the axis. Okay, spend up to 15 to 20 minutes collectively. Okay, there's just 5 of them. Okay, I'll do trace. So you return Einops dot Einsum. How much it's a 2D array. Right, we do this whenever the row and column match, you sum them up. Because that's the rule, right? Omitting a letter means that the axis will be summed over, summing over rows and columns, but only when they match. And this is matrix and a vector multiplication, right? So this would be mat and vec and ij. So this m cross n. This needs to be n cross 1. Actually, and to get an m cross 1 vector. Let's actually test these two. Yeah, Now let's implement this matrix multiplication. You have matrix 1, matrix 2. They need to satisfy this, and we need just sum over j for each icon. Okay, and here we do inner product. Say there should be the same length. I think this should work. Yeah. Finally, right, so this combines rule 1 and rule 2 above. We've repeated an index in both the input tensors, so these elements will be multiplied and have these products, and since we've skipped it in the output, it means they will be summed over, and that's what product is. Outer product, no star line, sum 1, 2. Guess they don't need to be of same size. Makes sense. Guess we are done. I'm going to uh, rename this. Yeah. Let's check if it has all our changes. It does. Go back. Guess I can remove this. Move this file. Yep, we're good. So yeah, we'll see you next time, where we'll be doing the next section of Arena. In the first chapter, chapter 0, some called ray tracing. Alright.